Hello everyone and welcome back to another minute concept. Well, this time an in-depth concept on calculus, particularly limits and how to solve them. So, like I mentioned in our minute concept on this topic, we have three different ways to solve for limits. So, the first and the most common that we're going to be using throughout this video is substitution, where we directly substitute the value in our limit statement. For example, let's say that we have the limit as x approaches a of the function f of x. When we substitute a into f of x, this will basically be the limit. So that tends to happen, and that tends to be true. Now, I'll be talking about the tests on that in another video, but basically that's substitution. And we also have factorizing or factorization. So factoring followed by substitution. So basically it just goes back. And we also have table of values. Now the table of values is the longest one to do, but in some situations it is necessary, particularly when we are dealing with limits that are approaching infinity. So let's try and understand substitution, factoring, and table of values one by one. So like I said here, this is what we're trying to get. Because in order for a limit to exist, there needs to be these conditions. So every limit has a left and a right side. So for example, let's take this line here. Each limit has a left and a right side. If I have this point here, we need to make sure that the point that our graph is approaching from the left and the point that our graph is approaching from the right are the same. And this is listed as our limit from the left and from the right, or our one-sided limits. One-sided limits here. And one-sided limits are denoted like this. If it's from the left, let's use this again, limit as x approaches a. If it's from the left, we put a minus sign. Now on the right side, if we're going to approach from that side, we're going to be getting the limit as x approaches a from the right side. Now, what is the condition here? Why do we have to get both of those limits? Well, of course, if they're not going to be at that same point, if they're not equal to one another, hold on, let me write it here. If the limit from the left is not equal to the limit from the right, then there is no two-sided limit. Or basically this has this statement right here. This statement will not have a value, and we can conclude that the limit as x approaches a does not exist. And this is the notation, or not really notation, but this is the standard way of writing that the limit is not there, it's not existing. And how do we determine, or what are the instances when limits do not exist? Okay, so for this we're going to be going back to rational functions and polynomial functions. Alright, so just a quick rundown on how this works. Take for example a polynomial function of, well, okay, this line here. Let me delete this. I'll shrink this one so that you guys just remember on the side. Any polynomial function, let's say f of x, where f of x is a polynomial like x plus 2, the domain of this function is all real numbers. So when you see a function like this, the limit will always exist. Unless, of course, the question states that there is a hole. Well, sometimes it doesn't really, it's not a problem if there's a hole, or it's not a problem as well if, for example, they state that there is a piecewise function. Let's say this function here where it's a polynomial, this is only for this is only for when x is less than 0. And when x is greater than 0, we're following a different formula here, which is x minus 2. Now, these are two different things. We cannot follow our idea that the limit always exists just because it's a polynomial now. The domain of all real numbers might not be true. And this is simply because, if you look, there is no value that describes 0. So right now it's missing. What is the value when we're at 0? And this can be solved with limits. Now look here. Piecewise functions are one of the trickiest types of questions. So we'll apply our learning of substitution and factorizing with this type of question first. So we want to get the limit of this piecewise. Let's use the limit as x approaches 0. Now, how do we approach this question? We have a piecewise function again here. Let's put the brackets. We have this piecewise function and we don't have a value at 0. Because if we had a value at 0, it would actually be easier to evaluate the function instead. But we can use the limits to understand this. Now, when we're going to get the left side limit, like we said here, which formula are we supposed to use? Okay, now, when we're approaching something that's less than, or when we're talking about something that's less than a certain number, and our number in question here is 0, by the way, that means we're on the left side of it. On the number line, being less than a number is on the left. So this will allow us to solve for the limit from the left. And when we're greater than a number, we're on the right. So this will allow us to solve for the limit as x approaches 0 from the right. And how do we solve for their limits now? Using the fact that we're supposed to use these formulas, we're just going to copy and paste this first. And we're basically just going to substitute 0 into both of them. So the limit as x approaches 0 from the left side is denoted by x plus 2, that formula. And if we're going to go the limit as x approaches 0 from the right side, it's x minus 2. Let me use a different pen for this one. Let's use sign as well. X minus 2. So let's just put parentheses so that's clear. Now we're going to substitute 0 here. So 0 plus 2 and 0 minus 2. This will get us positive 2 and this will get us negative 2. Now, are these two equal? They are in fact not equal. So we can say that their limit as x approaches 0 of the piecewise function does not exist. Again, this is how you approach a piecewise function. Now let's say that we're given just one of these and that was our only function. We would get a definitive answer. For example, 0 plus 2. Let's say our function is x plus 2 rather, not 0 plus 2. If our function was simply x plus 2, we just get a line, and substituting 0, we'd get the limit as 2. So at the value of x, our graph approaches 2 on the y-axis. However, because it's a piecewise, we need to evaluate two different formulas from the left and from the right. And that's basically already applying limits on polynomial functions. We already did it twice. Now, what is another thing that we can do, or another thing we have to study rather, about limits? Okay, so not every limit that we're going to encounter is a piecewise function. We'll also be getting limits like this. We could get limits such as the limit as x approaches, let's say 4 of x squared minus 16 over let's say x minus 4 and x plus I don't know, let's just give it a random number, 6. Okay, so we're looking at the value as x approaches 4. Can we substitute 4 into this equation? You guys can pause the video to try. Okay, so if we substitute 4 into this equation, when we substitute, we have to we stop using the limit value, by the way. So let's try putting 4 here. 4 squared is 16 minus 16 over 4 minus 4, which is 0, times 4 plus 6, which is 10. This simplifies to 0 over 0. This is what we call an indeterminate form. Indeterminate is different from undefined. An undefined form would look like this: any constant over 0, or actually any term n over 0. This is undefined, so don't get those two mixed up. Indeterminate is when you have 0 on top and 0 on the bottom, and undefined is when you have any number or term on top and 0 at the bottom. Both of these are problems when it comes to limits. What this tells us is that on our graph, let's say that our graph looks like this, though likely it does not. Like, let's say this is our graph. This wouldn't look like that. It's probably parabolic or something, but what it's telling us is that there's a hole in the graph. If you recall topics from Gen Math, basically what it's telling us is that the function value does not exist at that point. And that is the root of the function. That's what makes it undefined. So, what do we do for limits like this? In limits where there are indeterminate and undefined forms, we can turn to factorization. Now, limits can be factorized. Functions cannot. Again, limits factorable. Function values, no. Because this will get you a wrong answer. Okay, when you have a function value, you want to substitute straight into it. So if you're given something in the test, for example, you're having a calculus test about limits, and it just asks you to evaluate a function, you're not supposed to factor the function. You cannot simplify it other than how it's written. I hope that's clear, because that tends to be a typical mistake. Now, factorization is a deep topic in algebra. Considering that I'm hoping most of the people who have watched this video understand the different basic versions of factoring, such as difference of two squares, or sum or difference of two cubes, and perfect square trinomials. I hope that you guys can get through this pretty well. Now, of course, if you guys don't remember this, I might make a video on this, though that probably will be a bit later. I suggest use online practices so that you guys can practice factorization, especially because calculus is really heavy on that. But anyway, difference of two squares, summary difference of two cubes, and perfect square trinomials are types of special cases where you can factor a certain term into smaller terms. Now, difference of two squares is denoted like this: a squared minus b squared is equal to a minus b times a plus b. Does this apply to our limit here? It actually does, because we have one square here. This is our a squared minus another square here, which is 4 squared. This is now b squared. So we can expand in terms of this. We can write our limit now as the limit as x approaches 4 of the function, hold on, let me shrink this, of the function x minus 4, x plus 4 over x minus 4 and x plus 6. Now, what do we do with this limit? Can we substitute immediately? Still no, because if we substitute here, we'll still get 0. But what factoring now allows us to do is we can take out redundant terms or similar terms on the denominator and the numerator. So we can take out x minus 4, we can take out the one on the top and the one on the bottom. So now we're left with the limit as x approaches 4 of x plus 4 over x plus 6. And if you look at it now, we have no issues substituting 4. So let's try that now. Let's substitute 4 in. So 4 plus 4 over 4 plus 6. This will get us 8 over 10. Simplified, that becomes 4 over 5. Thus, the limit as x approaches 4 of this function, let's just write it like this. The limit as x approaches 4 of f of x is 4 over 5, or 4/5. Our goal in factorization is to make the equation, or not equation rather, the function itself as simple as possible so that we can avoid indeterminate forms. Again, our no-nos are 0 over 0 and any number over 0. These two are big no-nos because we can't get the limit when we have that form. That simply does not exist. To put into perspective, 0 over 0 could be literally any number. That's why it's called indeterminate. No one knows what happens when you divide 0 by 0. And when you divide something by 0, for example, like 1 divided by 0, it's that thing that Siri says. How will I divide something with 0 friends? Does that mean that I have an infinite amount of things to divide? Blah blah blah. Basically, it's a huge gap in math right now. So you cannot do that. That's why we go for factorization. On the other hand, there is another way to solve for questions like this. So, let's go back to our original function. So this is correct. Now, another way to solve for this without factoring is table of values. Now, table of values is a very, what's the term? It's a very tiresome technique. And why is that? Basically, our table of values will always look like this. I'm going to change the function because that function is too complex to be doing the table of values method. When we're going to set up a table of values, we'll just have our function on top and the limit statement. And we'll have a setup like this. So, typically you'd have 2. This is for your left side, so this is the limit from the left. I'll just write a minus here. I'll write a positive here. And this is our x and this is our y. What we want to do here is we want to put values or inputs that are really close to what we're looking for, which is 4. So let's try listing down some first. So we're gonna go in ascending order here because we're coming from the left. So a far number, or a technically far number from 4 would be 3. And then we can go a bit closer. We can go perhaps 3.5. Maybe we can go 3.9. And then here we can go 3.99. And from the right side, we'll be getting infinitely close to 4 from the right. So we need to pick a number that's greater. We can go with 5. Then we can go 4.5 because we're getting closer to 4. We can go 4.01. Oh no, 4.1 rather. And 4.01. And now what do we do? Okay, before we get to that part, let's define our function. Let's make this x minus 4 over x plus 4 over x minus 4. Okay, so what we want to do here is we want to get the values of this function, and we're going to be listing them down one by one. And this is where the tediousness of table of values comes in, because really this is the hard labor way of getting the limit. So let's try. We substitute 3 first. We know that we can substitute 4 because this won't work. There's going to be an indeterminate value. Not indeterminate, rather undefined. We'll get 0 in the denominator. So let's try substituting 3. So if we substitute 3, we'll get 7 over negative 1. That simplifies to negative 7. So we'll just put negative 7 over here. Now let's try 3.5. We'll get 7.5 over negative 0.5, which is equal to negative 15. Because this becomes 2 over 1. Yes, so that's negative 15. 7 and negative 15. Alright, now how about let's try 3.9. 3.9 would get us 7.9 over 0.9. negative 0.1, and this is basically going to be 79, negative 79 rather. If I made a mistake here, I'm so sorry. I'm not the best with decimals, but I don't have a calculator at the moment, so bear with me. Again, this is just to show you the process anyway. And 3.99 will get another 9 here, but instead a 0.01, and this become 1, 2, 799, negative 799. And we're just gonna repeat the process for the right side. Why do we have to repeat the process for the right side? Because we need the values at this point here to be equal. We need them to be equal so that the two-sided limit exists. Now, we're going to find out if it's going to be equal or not now. So, when we substitute 5, we'll get 5 plus 4 equals 9. 5 minus 4 is 1, so we'll get 9. And our y value at x equals 5 is thus 9. Now, 4.5 plus 4, that's 8.5. Minus 4, that's 0.5. That brings us to 17. From 4.1, we'll get 8.1 over 0.1. That will get us to 81. And 0.01 would just make it 4.01, I mean rather, would just make it 0.01, and this one would be there. And we'd get 801, if I'm not mistaken, 801. So let me remove this. Basically, it gets infinitely larger. Now, this trend will continue on, so forth, as long as you keep typing in more 9s or more 0001s. Are they equal, or are they approaching the same point? This is infinitely growing. We can say that since this is infinitely growing, the limit from the left, hold on, let's move down. The limit from the left would now be, as x approaches 4 from the left, of f of x is equal to negative infinity, because it has a negative value. On the other hand, the limit from the right, as x approaches 4, is approaching positive infinity. Are these two equal? They are in fact not. So that means that the limit does not exist at x equals 4. And what we actually would have here is what we call an asymptote. A vertical asymptote, to be precise, where the left side is going down and the right side is going up. So it would look like this at x equals 4. So the left side would be going like this, and the right side would be going up like that. And there is an invisible line right here, though that line is not straight. Now that is basically the gist of table of values. Now, this method right here is a very, what's the term? It's a very time-consuming method. However, what most tests would ask you to do is to substitute certain values one at a time, or fill in the table itself with the values you want to try. I suggest to save yourself some time, do not spend so much time on the far values like 3 or 3.5, and you want to make things go straight to the point. You want the graph and the outputs to speak for itself. Put your values immediately as like 3.5, or from 3 jump to 3.5 or 3.75 for example, and just see where the graph is going. See where the outputs are going. That way you save a lot of time, especially if your test is a multiple choice test. Now of course if it needs solution, that's a different thing, but alas, there you go. So for this video, again, just to recap, basically we were able to describe what limits are and how we're supposed to solve them. We tried substitution in a basic piecewise function. We also tried substitution after factoring, such as in this function right here. And we also tried table of values in this function. Now, if I made any mistakes, please don't be afraid to let me know in the comments. I just want to know if everyone is going to be able to get the topic, and if there's anything you want me to retouch on, I can definitely cover it in a future video. So don't be afraid to let me know how you guys feel about the videos in the comments. And of course, I haven't really been saying this recently, but we're really near to 100 subscribers. So hopefully you guys can press subscribe if you guys haven't already. And more videos on limits to follow, particularly on the continuity test and some shortcuts that we can do to solve the limit. So thank you everyone, and I hope you guys learned something from this video, this in-depth concept on calculus, particularly limits. So thank you everyone, and goodbye.